Topic 5, counting techniques. As a quick review, remember that when the outcomes of a random process are considered to be equally likely, the probability of an event is the number of outcomes in the event divided by the total number of outcomes in the sample space. So it would help us to be able to count efficiently. Could we write out the sample space each and every time? Yes. Could it be a total nightmare? Yeah. So we want to be able to come up with the size of that sample space efficiently. And also be able to come up with, hopefully find some techniques to help us come up with the number uh, of the count of the number of times something happens in an event. So let's start with the basic multiplication rule. Let's suppose example 5.1 that there's a quality inspection and a quality control inspector wishes to select 4 parts, one from each of the bin. And bin 1 has little a, b, c, d, bin 2 has capital A, B, C, bin 3, and then bin 4. How many different ways can the 4 parts be chosen? Well, with what we know at this point, we would have to write out the entire sample space, which would be a nightmare. It would take a long time. You would have to do little a, then little m, and then capital M, and that's one of many, many, many combinations that could come out of this, or many arrangements. Let's not use the word combination, many arrangements that could happen. So let's say instead, let's think about this. If we've got bins and we have 4 bins, and we know this is, let's call this B1 for bin 1, and then bin 2, bin 3, and bin 4. We know that in bin 1, we're going to have the options A, B, C, and D. In bin 2, options A, capital B, and capital C. Bin 3, M, N, O, P, and Q. And then in bin 4, capital M, N, and O. So how many choices, if we're to randomly choose, we just stick our hand in, they're all shuffled around. How many choices are there in bin 1? And hopefully you think, well, there are 4 things, so there are 4 choices. If we do that for each of the bins, now we have a count in each bin. If we multiply these together, this is going to give us 180, and this is actually the size of the sample space. That's great. Would you have wanted to write out all 180 options? I know I wouldn't have. So here's a quick little review. What's the probability that combination, you can see them here, little c, little m, capital N, or little b, capital B, little n, big N will be pulled? I'm going to make it a little bit easier to write, I'm just going to call this event 1 or event 2. So the event is the 2 things together. So we want the probability of 1 or 2. Well, we know for each of these, the sample size is 180. So there's the count. Are these mutually exclusive? In other words, do they have anything in common? The answer is no, so that's good. How many times could this actually happen given these bins? And hopefully you look in and say, well, it's only one time that could happen, and only one time that could happen. These are mutually exclusive disjoint events. Number 1 and number 2 are because they have no outcomes in common. So we're going to use that addition rule for disjoint events. And we get 2 over 180, and that ends up being 0.011. Now that's a lot easier than writing out the entire sample space and noting that that can only happen once, which hopefully you should be able to see that fairly clearly. What's the probability on part C that a combination has part M in it? So probability, we want something to have part M. Now there are different ways to do this. You could say, well, there are 180 total, but I like to look at it even easier. I can see that the only bin that has any little m in it is bin 3. How many options are there in bin 3? There are 5 choices there. I'm just going to write this out a little different so we can see it, but there's only one m. So we just need to look at the bins that had, or in this case, the bin that had the little m in it. So this leads us to the multiplication rule of counting. Suppose the first stage of a process can be completed in n sum 1 ways. Further, suppose that for each way of completing the first stage, the second stage, they can be completed in n sub 2 ways. Then the first two-stage process can be completed. In other words, multiply them together. So this rule naturally extends to k stages, k being some unknown number, and it can be completed this way. And this is just what we did here. This is just the rule down there is just formalizing it. So before we go any further with counting, we're going to take a look at a classic probability problem.